assembly, we go from assembly language, super detail, to Haskell. That's quite interesting. That is very interesting.
Here's a cool time lapse.
So does anybody know how many weeks are left in the semester? Yeah. So there's 2 weeks left of the lectures or whatever, and then there's then finals week. So after this week, we're almost done. We are almost done. And unfortunately, so I went back over the calendar for the class on the class webpage, the list of lectures, and I modified it and updated kind of where we are a little bit, and then kind of what's left. And so we'll have 2 more assignments. So homework 10 will be the last assignment. And unfortunately, I think that it's unrealistic to think that we will talk about logic-based programming. It's not going to happen. We just don't have the time. Actually, I'm super depressed about that because, well, one, it always gets kind of saved for the very end of the semester, which is my own fault. And it's the coolest thing ever. So answer set programming is the coolest thing ever. And it's always really upsetting that we don't get to it. It's also one of these things where it's really probably its own class, like to really get into it and to get into the details and stuff. And so it always is shortchanged a little bit. However, this semester with the loss of the week and just the way things are going, we just won't have time. So maybe I'll be able to show a little bit, but there won't be a homework assignment, and it'll be if we do talk about it, it'll be very, very brief. So kind of a bummer, but that's all right. Okay, so today the plan is I'm going to talk about recursion some more in Haskell, and then go over how to do pattern matching. And when I say pattern matching, I usually include this notion of a guard. So it's pattern matching with guards, but I usually just call it pattern matching. So then homework 8 is due, and then homework 9 is posted and available for you to start on, except I still need to send the GitHub Classroom for it. So I'll do that later today. Then there's really not much to the GitHub Classroom. It'll just be 2 empty files. Okay, so you can really get started at any point. And then there also is a quiz. So it's on Haskell and the stuff that we've talked about up to this point. So it'll be available after class today, and you'll have until next Tuesday before class to finish it. And so it's kind of the same thing where there's like 25 minutes to do it. I didn't include it as a PDF file. I just put the questions in the quiz itself. So hopefully that'll help make things a little bit easier. And then, so in the class, in the syllabus, I kind of had committed to doing 3 exams. So we'll have our 3rd exam next week, and it'll be available next Thursday. And it'll be, I think it'll go smoother than the last one. And it'll just be on Haskell. It'll be on just the things we've talked about since the last exam. So it's going to be just a little bit more of a, kind of a longer quiz, like 3 quizzes or something like that. All right, so before I start talking about Haskell and stuff, who has a question for me? Or does anyone have any questions about where we're at, where we're going, what we've done, what's due?
I have a question.
Yeah.
Yeah, sorry, I think you already said it, but I didn't quite get it. The exam, you said it, what is it going to be covering? Exam 3?
Oh, I'll talk more about it on Tuesday.
Oh, okay.
Either Tuesday or Thursday of next week. But it'll only be covering what we've done like since the previous exam. So it's just going to be on Haskell.
Just Haskell. Okay.
Well, it'll only be on Haskell stuff.
Okay.
That's all. Yeah.
Gotcha. Thank you.
And the quiz is good in the sense that it's also just on Haskell. So, it's kind of a little bit of a warm up.
Does our write-up for homework 8 today, do we have to include a paragraph on the test cases that we've...
Yes, please, because yeah. Not the mathematician, the language. It'll be on the language. Yeah, so you do need to write up just because you're supposed to do additional test cases. And that's especially true for homework 9. Because I just give a couple, like a case or something, just to help you to understand what the function is you're trying to write. There's other cases that you have to consider, in order for it to be considered working. And it's, it shouldn't be, the write-up should just kind of explain your approach and just generally like what you did, but we do want to see like, oh yeah, you did test this stuff. Because if you don't test it, it doesn't work. If you don't test your function, if you don't test your stuff, it doesn't work. That's the assumption. So, yeah. Any other questions?
Also, is there like a best way to show the test cases and like the results for that?
I think just, so you can, start up GHCI and just, for each function, just kind of show how you called it and then what the result was, I think. And then, copy that or run script for that or whatever. Does that make sense?
Yeah.
You can just directly go into the terminal and copy all of your tests and then paste that, and it copies pretty well. Formatting.
Yeah,
wise.
I think that works a lot better today. So that's probably the easiest thing is just, run it and then copy what you ran and turn that in. Yeah. It's not meant to be onerous.
Quick question. I know the exam is out next Thursday. When is it due by? Do we have like just to another class period or?
I think I'll make it, I'm going to have it so it'll span 2 weekends. So probably it'll be due like a weekend, like the following Tuesday, or no, not the following Tuesday, the Tuesday after. Does that make sense? So you'll have 2 weekends to do it. You'll have some time.
And then do we still have a final?
We'll still have a final. Yes. and I'll talk about that later. Yeah, we'll still have a final. And it'll be cumulative, the final. Again, so like exam 1, exam 2, exam 3, each one of those is was worth just 10% of the final grade. So they're meant to be like kind of lower stakes, right? And then the final is worth more, so it's worth I think 20%. And I'm going to try to get back for exam 2. I think grading things on Blackboard is like one of the most soul-sucking exercises there is. But I'm trying to push myself to just do it. All the grading, all the stuff on Blackboard, I'm trying to do it. It feels like you're on an assembly line because you you'll have this stuff and you grade it and it's like next, and it just shows you another one and it's next, and it's just it's not the funnest thing. It's not the best interface for doing it. But anyway, so I'm hoping to get that back. Although again, there won't be anything from exam 2 on exam 3. They're decoupled. But I think you'll need exam 2 and 3 to help with like studying for the final and stuff. Any other questions? Okay. So last time we basically stopped where we were just starting to talk about recursion, and I think the best way to kind of do this is just to do it as examples. So I'm just going to go through some examples of recursive functions in Haskell just to kind of give you a feel. And it's kind of a warm up. So one example is the exponentiation. So like exponent. So for example, the function would be like power xy, and this would compute x to the y. So x raised to the y. So then here's how we could define it. And again, we're using if then else. So our goal by the end of today is to not have to use, or to only have to use if then else in very limited cases. Okay, so we really don't want to be using if then else, but for now we're using it. So so we have a base case here. So if y is 0, so we're only going to consider powers that are 0 or larger. So if y is 0, then what's the answer? What's x to the 0? Somebody, anybody?
1.
Good, 1. Otherwise, okay, we're going to take x and we're going to multiply the result by the power of y minus 1. And there we go. Okay, so then whenever we define a function, we always want to know what the type is. So in this case, it's a little bit complicated. So again, Haskell's going to try to infer what the type is, and there's some hints here. Well, one is just like how many arguments does it take? Another one is what operators are used in the function and on which arguments. So here, like we're using equal equal. We're also comparing this to a number, to a constant. This is another constant, and we're also using this times operation. So it turns out that in this case, the type that Haskell infers is A to B to A, okay, where A is a number, B is a number, whoops, and because we're using equality over the second argument, B has to support equality. So this is a great example of kind of a very generic type that Haskell infers for us. And one of the things to notice is that it actually did, what you would think, in terms of, if you think about what this power function does, is really this can be a different kind of a type than this. So for example, I could do like 3.14 squared, right? And where this is like a float and this is an int. Probably what we really mean here, though, is that this B type is maybe an int. Maybe we really mean for it to be an int. So this would be a good example of a case where you would actually want to explicitly specify the type and change the type that Haskell would infer to enforce, because Haskell inferred a more general type than what we're intending here, I would argue. And so, to do that, to further constrain the type or to explicitly specify the type, the convention is you just put the type declaration above the function itself. So if I was going to put this in a file, for example, I would say that the power function here, in this case, has the type, it depends on what I'm trying to do, but let's say A can be any number type. So I would then say that A has to be a number, and then the type is A to int to A. And in this case, this is a more constrained type than what Haskell infers. Any questions about that? So here we're further constraining really what can go into the function in terms of types, but to more better express our intent with what the function is supposed to do. As long as the type that we declare is compatible or a subtype of the type that Haskell infers, everything is fine. And it won't give you a warning or anything like that. If the type that you declare is incompatible with the type that Haskell infers, it's going to complain at you. So in other words, Haskell doesn't trust what type you specify. Haskell figures out the type and then checks to see if you got it right.
So type class constraints go in the type constraints section with the equals greater than, and if it's just a type, it can go in the parameters and return.
Yes, that's right. Exactly, yeah. So we can't put type constraints in the actual type, they're constraints. So the type classes are used as constraints. The actual types are used in the type itself, if that makes sense. So here, int, so that's a good question. That's something that people make a lot of mistakes on. So the int is a concrete type, right? It's not a type class, it's an actual type. And so it can go on the right-hand side of the constraint, whereas all the type class stuff goes on the left-hand side of the type constraint. And I can't use num here on the right-hand side. So in general, it's really good practice whenever you define a function to also give the type that you think the function should have or will have. And the reason for this is that it's a way to kind of sanity check your function. So if this is the type we want power to have, then we declare our power function. If we made a mistake here, or possibly in the way we defined power, Haskell's going to tell us. So it kind of has a similar effect of typing in a normal language, It's just a little bit different in the sense that Haskell's not going to take our word for it at all. It's going to check every single thing to figure out what the most generic type is, and then uses what we gave as kind of a, hey, did they get that right? Check. Okay. All right, so as another example, my notes are off a little bit, is concatenation. Excuse me. So we're going to define a function called concat. We're going to name it concat. It's going to take two lists, x's and y's, and basically it's going to compute the actual concatenation operation in Haskell, which is the plus plus. So again, it takes two lists, creates a new list where x is in the first half and y is in the second part. Okay, so we're going to try to define concat, and it actually is very easy to define recursively. So I'll just show you that definition. So here, actually, somebody tell me what is the type of concat? We'll eat our own dog food. We'll do what I just said is good practice. So what's the type of concat?
List of char, list of char, list of char.
So that's close. That's more specific than concat actually is. In Haskell.
Is it like list A to list A to list A? 3 list A's?
Yes. So it can be a list of any type can be used in concat. So you give it 2 lists of any type A, and then it's going to return a new list of those same values of the same type. Okay, so this would be the type, and then basically what we're going to do is we're going to define concat using cons. Okay, and the way that's going to work is we have 2 lists. We can say, yes, we can say concat equals plus plus, but we want to define it from scratch, right? We could say concat equals plus plus, but this is just an example where we want to use recursion, and concat is a great recursive function to look at. So the way that you typically see concat working or defined is you iterate through the first list, and you take an element out, and then you cons it with concat applied to the tail of x's. So you just keep doing that over and over again until x's is empty. So if x's becomes empty, that's a base case for us. What should the result be? If x's is empty, what should the result of concat x's y's be?
Y's.
The y's. Okay. Otherwise, now we're going to do the recursive step. So we're going to take the head of x's, and we're going to cons that with the result of calling concat on the tail of x's and the y's. Okay, that's the recursive function. In the lecture notes, I go through kind of a derivation or an evaluation of this. So I think that's useful to kind of go through, just as an example. All right, so we're gonna define another function, which is also kind of like a traditional recursive function that people like to define, and it's called flatten, like smash, flatten. And the basic idea is flatten takes a list of lists and it nests the lists. So for example, if I give flatten the list with the first element being a list 1, 2, and the second element being a list 3, 4, the result of this is going to be a list. We kind of unbox the lists, so the result is going to just be a flat list, which is 1, 2, 3, 4. All right, so I'm going to try to give you a definition of flatten here, and you can tell me if it works. Okay, so if x's is empty, right, then we basically don't do anything. Otherwise, we just return x's. We're done. Otherwise, we take the head of x's, and now we're going to use the actual concat. We're going to concatenate the head with the result of flattening the tail. So the idea would be if I call flatten on this list 1, 2, 3, 4, then I'm going to take the head, which is 1, 2, and I'm going to concatenate that with the result of flattening the list that contains the list 3, 4. Right? And then on the next step, it's going to be 1, 2, 3, 4, and then flatten the empty list. And that just returns what we passed in. So this would be 1, 2 plus, or concatenated with 3, 4, concatenated with the empty list. So, coming back to our definition here, does this work? Do you think that this is a good definition for what we're trying to do?
Yep.
Okay, good. At least one person said yes. So it turns out that there is a major problem with this function. If I type this into Haskell, it's going to respond, no way. It gives me a type error. This actually gives me a type error. Well, that's so weird. I didn't even specify the type. How can this be a type error? So it turns out Haskell, actually before I go there, does anyone see the type error? Does anyone see the problem?
Could it
So again,
be,
oh, go ahead.
could it be that head is not very compatible with a list of lists?
No, that's not the problem.
Is it?
That's not the problem. It's close.
Is it when you return XX? Is that because down in your example you show it as an empty string, but does that convert to the same thing up above when you return then XS?
Oh, here?
Yeah.
Here?
Yeah. Is
Yeah.
it equivalent to like the 2 brackets?
Yes. Okay, good. So here's this is actually quite interesting, and there are some limitations to what Haskell can do. This is one of them. The problem here is what's called, the error that you're going to get is what's called the occurs check. And the basic idea is Haskell takes what you give it, right? Like we said that before, and then it tries to infer what the types are. And in this particular example, Haskell gets confused. It can't infer a type for the function, and it has to do with this occurs check. So the basic idea is, if you look at the definition, what we're saying at this point is that the input type has to be the same as the output type. Okay, just looking at it, Haskell doesn't know, oh, in this particular case, because X's is empty, that in this case, I'm just returning the empty list. It doesn't know that at this point, X's is the empty list. The only way it could know that is if it, in general, I mean, maybe in this case it could work, but in general, it's not going to reason about the values. Just like when we wrote the type checker, like nil was an example of this. Like we're not looking at the values, we're just looking at the types. And so in order for Haskell to actually figure out that X is here is null, it would have to, in general, it would have to run the code, right? So now we're not type checking anymore, we're actually executing. And so, and that's not the point, we're trying to infer the type. And so what Haskell sees is that X's was input to the function, and now it's also output. So X's is both an input type, whatever the type of X's is, it's also the type of, it's also the output type, or has to align with the output type. Okay, so here we're calling the head of X's, and we're doing a concatenation. Concatenation requires that the left-hand operand and the right-hand operand are of the same type, and they both have to be a list type. So if X is, let's say we start off by saying, well, X's has the type A, a list of A, then it has to be the case that because of this plus plus with the head of X's, that X's also has to have the type a list of something, which has to be a list of A in this case. And so here's where Haskell gets mixed up, is that these two types have to align. And in this particular case, it's going to try to align A to the type list of A. And in order for that to be true, this over here actually has to itself be a list of A. But if A is a list of A, then it also has to be the case that this is a list of A. And it'll just keep doing this, and it just keeps getting bigger and bigger, and they'll never actually align. So this is what's called the occurs check. So what we have to do in this case is basically break the input type from the output type. We have to break these two things apart. And the way to do that, in this case, to get rid of this, is to change this to what it actually is doing, which is returning the empty list. And now at that point, if we make that change, everything will work fine. We have to break the connection between the input type and the output type. Okay, hopefully that makes sense. There's some more detail in the lecture notes that kind of explains this in more detail. So then if we're going to give the type of flatten, so flatten takes a list of A's and now returns a list of A. So that would be the type of flatten. This is what Haskell couldn't infer because it was trying to align the input type and the output type because we had X's here. Okay, any questions about that, or do people feel okay about kind of recursion in Haskell? I mean, it's really very straightforward. I think that's the only hang up, maybe. Any questions at this point? All right, so we're going to move on to this idea of pattern matching. And in my opinion, pattern matching is like one of the really cool things about Haskell. So when I was an undergrad, I took a programming languages class, which was a lot different than this one, but we learned a language called ML, which is kind of a precursor to Haskell, sort of. And in ML, isn't as nice as Haskell, I would say, but it does pattern matching. And when I saw that in ML, I was hooked. I just thought that was the coolest thing. I was so glad that I saw this because it makes using recursion and just problems related to recursion so much easier to think about and to program. And so, so Haskell fully supports pattern matching, and I'm going to go through just the basic idea and then give some examples, and that's a big part of the homework assignment. So in pattern matching, the basic idea is that your functions, instead of defining like one kind of big function using if then else, is you basically define your functions as a series of equations. So here, this is an equation or a series of bindings, and you do it by case essentially. So here, we can see it with the if then else. So there's one case where x is null. Okay, so that would represent one pattern or one binding in the sequence. And then we have the case where, then we have the case where x is not null. And those would be two different patterns. So instead of using an if then else, we can actually break it into two definitions of flatten. Each equation or binding defines a different what I call the input pattern. Okay, so I'm going to give a simple example. Let's say we want to define our own version of not. So we'll call it I think I already did this one. All right, anyway. So my not. So it takes a value. If x is true, okay, in other words, if x, then we return false. Otherwise, we return true. Okay. This is silly, but that's fine. Doesn't matter. So basically, my not takes an x, checks to see if it's true. If it is, then it returns the opposite. Otherwise, it returns also the opposite. So in this case, there's basically, this is a very simple case where x can actually only have two different values, right? X can either be true or x can be false. And so we can define my not in this case using two different patterns. And in this case, there are two different, what we might call value patterns. True is one and false is the other. And so the way that this would work in Haskell is you would say my not. If my not takes true, then what do I want to return? So if my not takes the value true, what should the result be?
False.
False. Okay, so that's one definition of mine. That's one of the definitions of my not for this particular value. Okay, and then the second one, the second series, the second equation, the second binding would have the opposite value, which is false, in which case we want to return true. So here we're defining the function using pattern matching because we use we have the same function defined like twice, it looks like, but really what we're saying here is that it's the same function. We are defining it by pattern, by case. And so from Haskell's perspective, it has to like figure out how to actually execute my not, this function. And so the way Haskell does this at runtime, it uses a certain kind of model of computation for pattern matching. So what Haskell does is it basically, so the basic idea is it goes to the, so if I say my not of false, so I write this, I have my not defined, I'm in the interpreter, I say my not of false. So what Haskell does is it looks for all of the my not bindings, right? And it basically starts at the beginning of, let's say, your file, and it searches line by line until it comes across the first definition of my not, the first my not binding. Okay, and then it looks at what value was provided, and it tries to match it with the value, with the pattern in that binding. So in this case, because they're both values, we can see that that's not a match, right? It's not false and true. They're different values. They don't match each other. And so in this case, Haskell's gonna say, well, that's not a valid pattern for this function call. And so then it moves on to the next one that's available, kind of to the next line until it finds another my not definition. So then it gets to this one, the second one, and it does the same thing where it tries to align the value that's provided with the pattern. In this case, it's just two values, and we can see that they're the same value. And so here, excuse me, it found a match for the pattern, and then it's going to replace this with the right-hand side. So the key thing is it's going to look kind of one pattern at a time. When it finds a match, it evaluates and then stops searching for matches. It's done. Once it finds one match, it's done. Doesn't need to find any other matches. This is not true of all languages. So in particular, in Prolog, Prolog also has pattern matching. However, Prolog is different in the sense that when the Prolog computation model finds one match, it does the evaluation, but then it keeps looking for matches. So that's like the core difference, one of the core differences between a functional programming language and a logic-based language like Prolog. It is this idea of, they both support pattern matching, but the model of how that works is very different. I would say in Haskell, it's very simple. It's not quite as powerful as in some of the other languages. Okay, so I'm going to give another example, but this time I'm going to use pattern matching. So I'm going to call this mix1, x's, y. So it takes two lists. So it checks if the first list is empty or if the second list is empty, then it's going to just do the concatenation of the two. Okay, otherwise, it's going to take the head of the first one, cons it with the head of the second one. I'm running out of room. And then it's going to call mix1 recursively on the tail of x's and the tail of y's. Okay, so just so we can understand what this is doing, if I call mix1 of two empty lists, what gets returned? So you have to go real quick. So somebody just tell me what gets returned.
The empty list.
Good. Okay, so if the first list is non-empty, but the second one is empty, what does it return? Somebody else? Tristan.
The first list, 1 through 5.
Okay, again, if the first list is empty, but the second one is not, what's it going to return? Somebody else.
They'll return 246.
Good. Okay, so now if neither of them are empty, they're both non-empty, what gets returned?
One, two, three, four, five, six.
Yes, so it just interleaves the two lists. So 1, 2, 3, 4, 5, 6. Good. So let's say we would like to define mix 1 using patterns, okay? And so here, this kind of gives us a hint about what the patterns would be. Also, if we look back at the actual definition, we can kind of infer what some of the patterns are going to be, okay? So, at the core of it, again, if one of the lists is empty, we basically just return the other list. It doesn't even matter what the other list is. So in some sense, like this is not a special case. It's really handled by the other cases because if one of the lists is empty, then the other list just gets returned effectively. And that's basically what this first if is saying. So we're going to call our new function using patterns mix 2. So in mix 2, if the first list is empty, then we want to return the second list. Okay, that's one pattern. Then if the second list is empty, we want to return the first list. Okay, and then if the first list and the second list are non-empty, then we need to do the actual computation. So we would say like head of x's, head of y's, and then mix the recursive step, mix of the tail of x's and the, sorry, I'm running out of room, tail of y's. How do I know at this point that neither of those are empty? Actually, it's true. If we ever get to this pattern, how do we know that x's and y's are non-empty? We can guarantee this. How?
It already tested, basically in the previous two cases, if x's had been empty or y had been empty, it would have already executed by that point.
Exactly. So if x, let's say x is empty, so we'll never get to this line because we would have first matched, the first pattern would have matched, and according to Haskell, once you find one match, you're done. Okay, and then similarly, if y's was empty, then the first pattern wouldn't have matched, assuming x's is non-empty, but the second pattern would have matched, and so we'd never get to the third pattern. This also sort of suggests that in some cases, the order that you define the patterns is important. So for example, if in my if I did this, okay, then the rest of the stuff, if I reordered these and I put the last pattern first, I'm never going to call the second two patterns. right? Because everything matches with two variables, right? I can bind anything with two variables. And so this is a bad example. Like, don't do this in this case because we're basically overshadowing the second two patterns. They'll never get used in this particular case. So when you're defining functions using patterns, you have to be cognizant of the order. Sometimes it doesn't matter so much what the order is. So for example, it doesn't matter in mix 2 whether the first pattern is first or the first pattern is second, right? As long as these two are first, we're fine. Any questions about that? Okay. So now we're going to get, actually I'm going to, we'll just keep going. So now we're going to do some even fancier patterns, which have to do with lists. So one of the things that you can do is there's special kind of notation to where, sorry, let me go back for a sec. So one thing to notice is that using patterns, so in this case, using patterns allowed us to get rid of this messy if then else stuff. And that's generally the case. So there are sometimes when you do need, or you might need if then else. Okay, but in general, it's very rare once you start using patterns and guards. Okay, so here we're just looking at a pattern. So we got rid of this if then else stuff. So now we can even go farther. This stuff is really messy, I would say. This head of x's, cons, head of y's, cons, mix 2, blah, blah, blah. Like, we're calling a bunch of stuff. And really, it'd be great if we could also kind of dig into this list. We know it's non-empty, so what would be nice is if in the when we're doing our patterns, if we could say, hey, I want the head and the tail, but I want to match on it here, so that I don't have to call head and tail. That's just annoying. And so it turns out that in Haskell, you can use the cons operator on the left-hand side of an equals, and instead of doing list construction, it actually does list destruction. So I'm going to show that as an example. So I'm going to call this mix 4, and the first two patterns are actually the same, so nothing changes here. Those stay the same. But my last pattern I can significantly simplify by using the cons operator as a destructor, a list destructor. So I know both x's and y's at this point are non-empty. And so here I'm using the destructor syntax to match on the head and the tail of each of the lists. And so now I can use the head x directly instead of having to call head and tail. So I would take the head, I cons it with y, and then I cons it with my recursive call. And in this case, again, I don't need the tail operation. I just pass in x's and y's. So the syntax is a little bit weird because it looks like I'm consing, but again, whenever it's on the left-hand side of an equal sign, you're actually you're tearing apart the list. You're deconstructing it, or destructing or deconstructing. Sorry. And then on the right-hand side, we're building back up. We're constructing the list. So they're the same symbol, but they actually have different meanings when they're on the left-hand side versus the right-hand side. Let me fix this. My grammar is atrocious. It gets worse than this, believe me. Okay, so then the other part of this is when you're doing list deconstruction, the parens are required. When you're doing this on the left-hand side. When it's on the right-hand side, they're not required, right? It's like normal cons, but you have to have the parens when you're doing list deconstruction. Okay. So just to make it abundantly clear, I'm going to do just a very super simple example. So I'm going to define my own version of the head function. I'm going to call it f. So here I say f of x's is equal to the head of x's. Okay, so that's my head version. I'm just calling it f. How can I do this without calling head? How can I redefine what head is here without calling the head function?
On the left-hand side, do you replace the just x's with parentheses x colon x's, and then equal?
Okay, so now I deconstructed it, and then that equals x. So these are equivalent. Okay, good. So now, let's say I want to define a function g, and g is basically just another name for taking the tail of x's. Okay. How would I do this without calling tail? Somebody else.
Is it the same as before except you're equaling XS?
Exactly. So here, I deconstruct the list, and then I just return x's, the tail, which is the tail. So again, these two are equivalent. So there's a couple things I just wanted to point out. So one, let's say I come back to G here. So what's going to happen? Okay, so this is my only pattern, right? I have one pattern. What's going to happen when I call this let's say I'm in the interpreter? Well, I'll tell you. There's only one pattern. So what Haskell's going to do is it finds the pattern. Okay, it's going to find the pattern, and then it's going to try to match this part, the argument, which here we're doing list deconstruction, with what we pass in, with the value. In this case, this is an empty list, and this is saying we have a head and we have a tail. So this is only going to match if we have a list with at least one thing in the list. There has to be at least one element in the list in order for this to match, to pattern match with a value. Since the empty list doesn't have any values in it, these two things are not a match. Okay, this is not going to be a match, which means that this pattern fails. It's not a match for our function call. Since there's no other patterns, Haskell is going to complain that this is basically undefined because it couldn't find a matching definition. In this particular case, if this is all the definition of G that we have, just this one pattern, this is what's called a non-exhaustive pattern or function. So we don't consider all the possible cases. The one that we're missing is an empty list. Are there any questions about that? So in this particular case, one thing we could do is we could define, so we know the tail function, we tried this, if we pass an empty list into the tail, it actually gives an exception. That's just how tail is defined. So we can do that in this case by using the error function. And then we would define our pattern. So here's a question for you. Can I change the order of those two patterns?
No.
I can't?
I'd guess yes.
You can. In this case, you actually can, because they're disjoint, right? So I either have an empty list or I don't have an empty list. If I don't have an empty list, it's never going to bind with the empty list. And if I have an empty list, it's never going to bind with non-empty list. Okay. The other thing that you can do, which is pretty cool, is I don't know why we do it in this case, but let's say I define another function h that's like maybe tail, but it takes the tail of the tail. So in this case, you can specify something like this, and then return the tail of the tail. So here in our deconstruction, we're actually saying that what H takes is a list of 2 or more elements. Okay, so you can, this is kind of a trick that you can do. Again, if I just had this is a non-exhaustive pattern, right? And if I put an empty list case, it's still a non-exhaustive pattern because it wouldn't be able to support a list with just one element in it. Okay, so moving on, the next thing that is very convenient is in Haskell, there's this notion of what's called a wildcard. And a wildcard has the symbol underscore, and it stands for don't care. And you can use it in places where you would otherwise put a variable. So in our example, when we're defining our function f, what we had was x's equals x. Okay, that's our version of head. So in this case, we don't use x's on the right-hand side at all. Right? We don't use x's at all in this. So in some sense, our x's is a don't care. We don't really care what the tail is. We're not using it anyway. And so it's better style to replace this and use a wildcard. And what this says is basically, I'm just matching on the head of the list. I don't care what the tail is. I'm not going to use it. And then in this case, I'm just returning x, the head. Okay, and I can do this. I can do the same thing with G. So again, G, the way we define this, just returns the tail. So in this case, we're not using x at all. We don't really care what x is because we don't need it. And so it'd be better style to just use a wildcard, an underscore. And this tells us right away that basically we're just using the tail. Like you can just see that right away. So this is considered good style. Any questions about that? So in your homework assignment, homework 9 and beyond, homework 10, whenever it makes sense to use wildcards, use wildcards. It's considered good style, so you should be using wildcards whenever possible. Okay. I wanted to show another. Actually, I'm gonna pass. There's another example where we define last and init using wildcards and recursion. Those are good examples to look at. The one kind of interesting thing with respect to this is if we go back, so let's say, actually, we don't really have a case for that. Let's say we had a pattern where we really care about exactly a one element list. So the difference would be like this is 1 plus elements, right? It's 1 or more, but there has to be at least 1 as a pattern. If we just want to match on the case where there's exactly 1 element in the list, we can use a couple different syntaxes. So we can say a list where we don't care what's in the list. We don't care what the element is in the list, but it's a 1 element list, for example. Okay, or I could match on that element if I wanted to. Another way to do this would actually be something like this, okay, or like that. But generally, that's a more preferred way to do the matching. Okay, so it kind of gives an example of this. And then there's another kind of exercise that you can go through. The answers, there's no answers in there, so you can kind of mess around and try this. Try these examples on your own to see if you can figure them out. And then there's one more thing I wanted to talk about in the remaining time. So, which is going one step farther with patterns, which is to use what's called a guard. So guards basically kind of go with patterns. So the basic idea is that a pattern, like we've been talking about, is a structural match. So you're matching on, parts of a list, for example, but you're not so concerned in a pattern. You don't really have a great way to specify, like, I only want lists that have certain, values that are within a particular range. You're not matching on that in a pattern. You're really just matching on the structure of the input. So with lists, for example, I'm interested in non-empty lists versus empty lists, or one element lists versus a list with 2 or more elements. That's what I mean by the structure. So whereas a guard actually gives you a way to specify a condition, like a conditional over parts of the pattern. So I'm going to give an example of this. So I'm going to do the drop function. So drop, if you remember, basically takes a number, n, and then it takes a list. And we're going to drop the first n values from the list. Okay, so if I have an empty list, I don't really care what n is. I just return the empty list. There's nothing to drop. Okay, whereas if I have a list with 1 or more elements in it, then what I want to do is I want to make sure n is a valid value. So it needs to be 1 or greater. So if n is less than or equal to 0, then basically I'm just going to return the list itself. I'm not asking to drop anything. So then to do that, I have to actually reconstruct the list, right? Because I broke it into the head and the tail. So here I have to return it combined back together. So if n is 1 or greater, then I do the recursive step, which is I'm going to actually do the drop, by not including the x. So I drop now one fewer element from the tail. Okay, so that's a pattern-based way to define drop. We defined drop before using recursion, but it was one big if-then-else. So we got rid of some of the if-then-else part. And now what you can see is we still have an if-then-else. So we'd really like to get rid of this. And the if-then-else itself is purely based on a condition on one of the arguments to the function. This condition that n is less than or equal to 0, for example. So this is a great case for a guard. This is when we would want to use a guard. So the way you would do this is you again use patterns. So I have my first pattern, which is just kind of the base case, or one of the base cases. And then I have the case where I'm dropping n elements from x's, okay, but in this particular example, n is less than or equal to 0. If that's the case, if n is less than or equal to 0, then I just want to return x's. Okay, so that's the first part of the conditional. And then I can, I have another pattern where I don't care what the x is because I'm not going to keep it. And here I know n is going to be 1 or bigger. And so then I just do the second part of the else. So I would say drop n minus 1 of x's. So I've defined drop now piecewise without any conditionals. But in this case, I used a guard to accomplish it. In general, when you're defining a function using guards, you can have multiple guards per pattern. So just as a simple example, and this is very apropos. So I have a function that basically takes a percentage, let's say, but as an integer, and I want to calculate what the letter grade based on that percentage is. So one way would be to have this big, messy if-then-else statement. Okay. Instead, we can do that whole if-then-else statement just using guards. So for example, if the percentage is greater than or equal to 90, then the student gets an A. Okay. If it's greater than or equal to 80, then it's a B. If it's greater than or equal to 70, it's a C. If it's greater than or equal to 60, it's a D. And then otherwise, it's an F. And so here, hopefully this makes sense in that a guard is really a conditional. So what goes after the bar here is something that returns or evaluates to true or false. So what this otherwise case is, this is just a binding for false. I'm sorry, not false. It's just a binding for true. And guards work very similarly to patterns. So, and it's kind of like a two-step process. So initially, Haskell's going to match on the pattern. And once it finds a match for the pattern, it's going to, if there's guards, it's going to go through and check each guard one at a time. And when it finds one that matches, then basically that's when it stops looking. And in this case, it keeps looking through the guards, and if it doesn't find it's always going to find a match in this case because the last guard has this otherwise case, which basically is just a name for true. Okay, so in this particular case, this is an exhaustive pattern based on the guards. So we only have a minute left, so I'll just do one other really quick example just to give you another example of kind of how this might work. So I'm going to define a function called pairs, and pairs takes a list, and then it basically just takes like sequential elements in the list and pairs them up. So if we have an empty list, it just returns the empty list. If I call pairs on a list with one element, then I can't do a pairing, and so I just return the empty list. And then I have the main case. So those are the two base cases, which is I have at least a 2-element list. When I'm going through pairs, I'm looking for elements that are next to each other that actually have the same value. Okay, so and then I represent those as a pair. So in this case, I would have two guards. So one is if x is equal to y. If that's the case, then I do a pairing. So I pair x with y, and then I call pairs on y put back with z. So it's finding all of the sequential pairings. And then otherwise, I'm just going to keep looking for pairs starting at y. So just as an example, if I call pairs of the list 1, 2, 2, 2, 3, then this is going to return a new list where 2 and 2 are paired,